In order to calculate the reactions at the fixed support of this built-in beam, we have to apply superposition and simplification because of symmetry and antisymmetry. First of all, we split the problem in two. The first case is going to be the symmetric geometry with the symmetric loads. In this case, the distribution of force in the central region, okay, P divided by A, and plus an antisymmetric case on the right with the forces P downwards and upwards, this antisymmetric loading. Okay, so the forces are P, and the distribution of force is P over A. Okay, so we are going to call these points A, B, C, cross-section C, cross-section D is the symmetrical plane cross-section, E, F, and G in the right fixed support. Okay, and we have to take into account that the distance between the fixed supports and the loads in the symmetric case, we have a distance between C and cross-section D that is A divided by 2, okay, and the distance between A and C is equal to A. In the antisymmetric case, the force P is located at a distance A divided by 2 from the fixed support, and the cross-section D is at A from cross-section B. Okay, so first of all, we solve the symmetric case, and then we solve the antisymmetric case with the simplifications we have, and after that we put everything together. If we analyze the deformation, we will have in the symmetric case something like this, some kind of this deformation, okay, with antisymmetric deformation in the case of the antisymmetric problem. Okay, always in the fixed support we have straight angles. So if we analyze the symmetric case, what we do is we cut the structure according the plane of symmetry, according to this cross-section D. So we have cross-section A, cross-section C, and E, and distance A and A divided by 2, as we analyzed it before, and we have the distribution of load that is that has a density P over A. Okay, P over A. And then when we cut the cross-section, we have to write the internal moments and internal forces. In this case, we have a bending moment that is MF sub D or M sub D. This cross-section is not E, is cross-section D, okay, in the plane of symmetry. And we have a series of simplifications that is that the slope of the cross-section D in the symmetric case is equal to 0. And in addition, we have that the shear force at cross-section D is equal to 0, something that we already know, so we don't write the shear force. We are going to use the equation angle of D equal to 0 to calculate the bending moment at D. Okay, so first of all, we are going to analyze bending in CD because of P over A, distribution of load. That is, we apply superposition between loads, and we also apply some kind of the split between the part CD and the portion AC of the structure. If we analyze the part CD with this P over A load, we introduce a fixed support at C, and we calculate the slope of D because of the deflection in this portion CD, and we apply the formula for the distribution of load or vertical load in a cantilever beam. So we have that the slope is QL cubed, in this case LCD cubed, divided by 6 EI. Okay, so we put the numbers. Q is P over A, L is A over 2, so cubed divided by 6 times Young modulus and moment of inertia of that cross section. Okay, so this is equal to P multiplied by A cubed divided by 48 times EI. Now, in order to calculate the effect of bending between A and C, what we do is we draw the part of the structure between A and C. This is bending in AC, and because of the distribution of load, that is because of P over A, distribution of load. So we write the fixed support at A, the portion to C, and we translate the equivalent forces, that is P divided by A multiplied by A divided by 2. This is the equivalent force, and we have a moment because the force is applied at A divided by 4 from the cross-section C, okay, the equivalent force. So we have this force and this force P divided by 2, and the moment P divided by 2 multiplied by A divided by 4. So the slope of of D with respect to C is the same value as the slope of C. So we have P over 2 multiplied by A squared divided by 2EI plus the effect of the moment P divided by 2 multiplied by A divided by 4 multiplied by the length, that is A, and divided by EI. Okay? And this is equal to PA squared PA squared divided by 4EI plus PA squared divided by 8EI equal to 3 over 8 equal to 3 over 8 PA squared divided by EI. Well, this was not the result of the slope at D because of bending in CD was not A cubed, is A squared, okay, because this is a slope. Okay, so we have to write the slope of D. The slope of D is equal to this is in this part is cubed, but in the final result PA squared divided by 48 EI. Okay, so we come back to the last effect, that is the effect of the moment. In this case, we draw the complete half distance of the structure of the symmetrical part in order to analyze the bending in A, B, C, D because of this internal bending moment at D. Okay, so we draw the fixed support at A, the complete portion from A to D. Okay, this is 3A divided by 2. This is cross-section A, and we have here the bending moment at D. So the slope of D, because of this bending moment, is the slope of the free end cross-section of a cantilever beam. So the bending moment multiplied by the distance divided by EI. Okay, so distance is 3A divided by 2, so minus 3 mf dA divided by 2 EI. Okay, so we have the complete slope of of d, the total slope of d, that is equal to 0, and the addition of the three addends we calculated before is pa squared divided by 48 ei plus 3 over 8 pa squared divided by ei minus 3 mf dA divided by 2 ei. Okay, so this has to be equal to 0, and this enables us to calculate the bending moment. Okay, so if we calculate the addition of the terms with PA, the result is 19 divided by 48 PA squared divided by EI minus 3 MF at D multiplied by A and divided by 2 EI. This has to be equal to 0. So we can write that the bending moment at D is equal to plus 2 over 3, 19 over 48 PA. Okay, so 48 divided by 2 is 24, multiplied by 3 is 72, so 19 divided by 72 PA. Okay, this is the result of the bending moment at D in the symmetrical case. Now, let's analyze the antisymmetrical case. We draw the first half, the half of the left. In the antisymmetric case, we have this vertical force P at A divided by 2 from the fixed support, and we have in the cross-section of the symmetric plane, of the plane of symmetry, cross-section D, we have the shear stress at D. Sorry, not the shear stress, the shear force at D. So the simplifications are that the bending moment is equal to 0 in this antisymmetric case, and the deflection of D has to be 0, and we are going to use this equation to calculate the shear force at D, this unknown. Okay, so bending, let's analyze bending in AB because of the force P. So we have the structure with only the force P, okay, and what we want to calculate is the deflection at D. So the deflection at D is going to be equal to the deflection at B plus the slope of cross-section B clockwise multiplied by the length between B and D. Okay, that is equal to A. So we can calculate this deflection of B by using the formula for the cantilever beam with a force P at the free end. The length of the cantilever is A divided by 2, so cubed and divided by 3 EI plus the slope P A over 2 squared divided by 2 EI multiplied by A, and this is equal to P over A cubed divided by 24 EI plus P over A cubed divided by 8 EI. Okay, so the addition of this is equal to this is equal to 1 divided by 24 plus 3 divided by 24, so 4 divided by 24 PA cubed divided by EI. That is 1 divided PA cubed divided by 6 EI. 1 divided by 6. Okay, so